So today we'll do some sort of basic groundwork, some results of some basic results, actually fairly deep results. But I just state them mostly. We'll first go through the classical version of those things are actually much easier, and then see what the importance is. So the point is that, and this is a philosophical thing, that computation must be performed using a small set of predefined primitives. So this is the philosophical point that, I mean, you can't have, it's not computation if whenever someone comes up with a problem, you say that, oh, you're asking me to solve primary testing. Now I have this big gadget with just primary testing. Here is the input, here is the output. That's not the thing. You have to have some small number of predefined things that you can do. You can do multiplication, addition, maybe if then else, things like that. Very small number, finite number, which should not depend upon the problem you're starting with. And then you write down your process in terms of, and it should be a small description. So that's the general thing, even in classical computation. So you start with a small number of primitives. All your computation have to be described in terms of those small number of primitives. Okay. So one specific way this is done in the classical setting is in the circuit model. So in the classical setting, so so, there are three things. So every Boolean function from say n bits to 1 bit can be written as a composition of, Boolean function. That act on uh, small fixed number of bits. So fixed as in it's not a function of n. In fact, how many like how many such things? In fact, we know what this is, right? So in fact, you can choose that and oops. So if you have not seen this before, it's a good exercise to try. Why? That any Boolean function can be written in terms of just and or easy just both. So and or and or both and or of 2 bits and not on 1 bit. Just with these, you can write out any Boolean function by composing them. So this actually satisfies this thing, right? That computation should be performed using a small set of predefined. So predefined computer is actually very small, just 3. And there is another thing, which is this is sort of important for practice, and that is so let me just number these things. 1, 2. The third thing, it's also important in practice that if someone else comes up with a different set of primitives, then you should be able to translate simply between them or easily between them. So the third thing is that if there is another set of such function, that is what which functions, so like um, these are functions acting on a fixed number of bits. Okay, such that if is within terms of function using circle. So I'll introduce some terminology here. With this density size. Yes. Then F can also be written as a this representation the CF means is a constant that depends only upon the family, not on the function F, right? Only on the family capital F. Okay, so
But then the fact that the family is complete, what is non-trivial about this?
yes, in this classical case, nothing is non-trivial about this. These are all fairly obvious facts. Right? So, yeah.
Even then, I don't see what is non-trivial.
No, in the quantum case or the classical?
Let's say what.
Yeah, in the quantum case, everything here will be very non-trivial. But I say in what sense? So, so in the classical case, so firstly, let's just say, so just to say, so these are important. They're very important for classical computing. In circuit model or any other one, programming language, whatever. But they're actually sort of trivial in the sense that, so in the classical world. Oh, by the way, I should first say what is size and depth, right? So, what is size and depth? So, everyone has seen a Boolean circuit, right? So yeah, so in a Boolean circuit, you have some input wires and there is a final output wires. Right? So the size is just the number of wires in things that are connected in like so the total number of internal wires. That is one notion of size. The depth is the length of the longest path that you have to take from going from the input to the output. So that is some notion of time. So basically, how many gates will you have to cross to go from input to the output? Okay. So that's the depth. Is that clear? So depth just means that I have to start with the input and I want to go to the output. So I draw a path with the circuit. And I mean, of course, you shouldn't come back. It's a directed graphic. It's like things are going forward in some sense. And I look at the longest such path. So it's basically saying, so take an input wire. How long will it take? How many gates will it have to cross to get to? The maximum such value of a circuit is the depth. The size is just the number of internal connections, like all the total number of connections, internal connections. So that is. So intuitively, it's very clear what size is and what depth is. So I'll just not try to more formally define them, but this is what. Okay. So in the classical case, these are all of these are fairly trivial results, right? So in the classical case, the way you prove these things is classical case, you prove item 2 and in fact the proof gives you both 1 and 3 for free more or less. Okay. So that is easy. So the way you prove 2, if you have not done it before, there's just one idea basically, which is that any Boolean function can be written as basically OR of ANDs in some sense, and that is should be see. Basically, the point is that it is one under a certain set of inputs. So you just have to take OR of those inputs. So that is the idea. So it's very easy, and so it's sort of a trivial result. So we don't even think about it basically. So in the quantum case, in fact, this becomes quite non-trivial. And the first thing is that already, even if I'm just looking at one qubit, there is not just a finite number of gates. In the Boolean case, when I'm looking at one qubit, there are like there are only how many? Like there's just two like, identical or not. In the quantum case, there are infinitely many. You can do any rotation. Like so even so it's not so there's certainly uncountably many gates just on one. So this whole idea, like even with one qubit, it's not immediately clear that you can get a small set of. So the point was here it's finite, and finite is really important in the quantum case also. You want to start with a finite set of primitives. So it's not clear that you can just take a finite set of primitives, even on one qubit, which will sort of let you go to any one of the things you want. So already some approximation will be needed. With any finite set, you will only be able to achieve anything approximate. That's the first thing. Then it comes to more than one qubit. Now again, you want to make sure that you only use gates that act on only finitely many qubits. But in the end, we want to make circuits that act on an arbitrarily large number of qubits. So this will also be non-trivial. So this whole idea of what should a complete family mean. So here and or are not called complete families because they're just anything can be any function can be written in terms of it, and the third property also works. That if you come up with some other family which is writing down f, then you will be able to translate into this family without only a small amount of overhead. So this property also is non-trivial in the quantum case. I mean, firstly, the notion of completeness has to be defined properly, and then the question is what is a complete set? So first, let me just state one result, which goes some way towards doing number one, okay, but not fully. So this is a result from so bunch of people. So this is Berenko, Bennett, Cleve, D. Vincenzo, Margulos, Sharp, Steter, and Smolin, and Weinfurter from 95. So and this says at least something maybe which is not maybe a bit surprising the first time it says that any unitary. So okay, maybe let me just forward this. So Back to the this will not be about um it will not be about how long it will take or something. It will just do the following. Any unitary on n qubits.
Okay, so I guess if you go up.
Yeah.
To the functions.
Yeah.
You're not really looking at functions as 0, 1 to the n to 0, 1.
No, I'm looking at that. Right?
But then why so for example, one thing that you will have to take care of is in a quantum gate, you will in a
But
quantum.
it's about classical. This one thing here about classical. It's no quantum.
But Boolean functions, you're not looking at them as 0, 1 to 0, 1. 0 to the n to 0. It's not a Boolean function.
It's about 0, 1 to the n to 0, 1.
Yeah, so when you say
in the quantum setting. Oh, okay. So the quantum setting now is not just Boolean function, right? I mean, we have been okay. So what is the analog of? Yeah. So in the classical world, the functions we were looking for are Boolean functions because our state space was okay. Yeah. So maybe I should. Yeah, so I jump. So in the classical world, what we are looking at is functions from 0, 1 to the n to 0, 1 to the n. But it's clear 0, 1 to the n to 0, 1 is fine because you can just do each bit separate. So that's it. So the quantum world was what we are looking at. So our state space is on n bits. We are going to look at arbitrary functions on n bits. And that can be written as composition of, or not just composition, just collection of single bit output function in the classical. But any computation in some sense is like that. I can take n input, n bit as input, and n bit of output, and I want to write on there is some big function there. And this function can be written as and or not, because each of its components can be written like that. That's the classical. In the quantum setup, now this function gets written by an arbitrary unit. Because now our state space is now our initial input is some vector in that big 2 to the n dimensional space, on which some unitary acts, and then we get some 2 to the n dimensional output. Yeah, that's right. So here, this is what it means. In the quantum case, F gets replaced by unitary U. Okay, so that's the cost. Okay, so now so now this result will make sense. So this can be written as a product of 1 and 2. Right now, I'm again saying that, so like arbitrary 1 or 2 duplicates. But in fact, the reverse is more. In fact, the only 2-qubit gate required is C. This actually is useful, right? So it's saying that essentially what you can do is if you had the ability to do arbitrary transformations on a single qubit, then combining those things and you can create any unit on any number. So having access to at least one 2-qubit gate is necessary, right? Why? This is true in the classical case also, but yeah, so because otherwise you just create if you start with the all zero vectors, you only create tensor product states. So that is clearly not going to include all unitary. So having answer to at least one 2-qubit gate is important, and it is like that's enough. Take the simplest 2-qubit gate, is C0. You have access to all single qubit unitaries. Then you can create any qubit unitary. So this is an exact. There's no approximation. So it's useful mathematically. It's not useful computationally. Right? Because in computation, it's not just enough to say, yeah, I mean, like, firstly, the biggest thing is that, like, even as I said, like, even on one qubit, it's not so clear. Like, you don't know, right? That, I mean, like, you don't want to say that, oh, please rotate the qubit by an angle, and the angle is represented by 100 billion digits of precision. So that's cheating in some. So this goes back to our discussion about Shamil's result and so on. That if you have to worry about this representation size issue also. So this is mathematically though very interesting. Right?
Could you repeat what is Shamil's result?
Oh, Shamil showed the following thing, which may sound yes. We showed that if you can do factoring, you can factor n using only polylogarithmically many arithmetic operations. That's what we showed. Sounds like all cryptography should break down. The point is that the numbers that will come up will be very large. And you will actually also look at the bit representation of the number.
And he did it along with Rivers and Edelman, right?
No, this is just this is very problem. We did this in class.
Yeah, he did.
Yeah, no, that is ours, that is different. So yeah, so Shavi showed that would be the result. So this result can be seen as some analog of the first point, but not quite because it's not giving you a finite set. But it's sort of like an analog of the first one. We'll think, okay, 1 and 2 qubit gates are enough. You don't need anything. But all 1 qubit gates you need. So can be seen. And this is sort of like a sort of a result you can try to prove by induction sort of. It's like you try to keep rotating things that the unitary starts looking like one since different components. That's how it works. But yeah. But really useful. Right now, it has uncountable many basic gates, although the uncountable ones are all small. They're only acting on one case. They're 2 plus 2 matrices. And the only other thing it needs is a CMOS case. Okay. So for this, so now if you have only finitely many quantum gates, you have an uncountable set. So can you ever? So let's say we just focus on one qubit. Suppose we start with just some finite set of 1 qubit gates. Can we ever generate all the unitaries? So this is an argument that people must have seen it. It's just diagonalize this. It's an output. The set of unitaries is uncountable. And whenever you write down, so you have finite set of gates, so any circuit you write down with those can be represented as a finite length string over a finite alphabet. So the whole set of all such things is countable. So clearly, most of those things you will never get. But Yeah, you can come arbitrary close. So that will be the situation now. So what we will need, so the notion of completeness now will be in terms of close, in terms of getting arbitrarily close to what we want to do. So we will so just by counting. You cannot be able to simulate. Um, approximately. Or approximation. And what should be the notion of approximation? So what does the unitary do? So the unit, what does the unitary do? It takes an input and produces an output, right? And then you do something with the output. And the things you do on the output are other, like either other unitaries or projections. So what you want is that the results of this post processing that you do should not change by much, right? If I so basically when I'm trying to approximate a unitary, I should do it in such a way that for any input, whatever new output it produces, whatever post processing I do, the result of that should not change by much, right? But the kind of post processing I'm allowed to do is apply unitaries, apply projections. So the results of these things are sort of length preserved. If I change the length, if I move to something which is only a distance delta in Euclidean norm, then the results of any of these things also change by at most delta. Unitaries change by exactly delta, projections change by at most delta. So what we want to say is that the projection should be such that that if I go from u to u prime, which is the approximation, for any input, u psi and u prime psi are close. Right. So what we need is that if we approximate u by u prime, then u psi and u prime psi should be close for any. So the approximation is u minus u prime. So this is the definition almost. It is the maximum. Actually, we can write maximum over all psi whose norm is 1. Like if we did norm is 1 of u minus so today the bars appearing on the left are different from the bars appearing on the right. On the right, that's just Euclidean now. On the left, it's a definition. This thing is often called a 2 to 2 now. Why 2 to 2? Because you're looking at things that have unit norm and then looking at the difference in norm. So you can define it for any norms, but are also called the operator norm. And it's actually a norm, right? And it's not even just a metric, it's actually a norm. I mean, the way I define it is actually just can define for any unit, not just a distance, it's also a norm. So we'll often just drop the 2 to 2 thing. This will be the thing. Okay. So in the homework, I think you have been asked to prove that if you take u and v and you look at u tensor v, u tensor I and v tensor I, the operator norm distance between u tensor I and v tensor I is same as the operator norm distance between u and v. So basically, it's nice in the sense that if I'm just adding extra qubit wires, it's not changing distance. Okay, so now we want to approximate in this, and so here is the result. It's called the Kitaev-Solovay theorem. Let me just. So now we can write on this thing. Complete. Okay. So the definition is that so let K integer and then a set S of K qubit unitaries set the complete cases. It is closed under inverse. So this is just a technical condition. You can take any close to the inverse. So if the unitary is there, its inverse also there. So if C naught is there, what else should be there? Okay, the C naught is there. Adamat is there, what else should be there? Adamat X, Z, Z. Yeah. So most of these things you looked at are their own inverses. So often this thing is not even a problem. But yeah, this is just technical. And this is the more important thing. Basically, any unitary on K qubits is well approximated. So yeah, and for every unitary U on K qubits and delta is 0, there exists a complex number Z, which is a function of delta and U of unit norm. And a positive integer L. Also a function of delta and U, such that there exists a finite there's the sequence written down between the Z delta U times U minus A1 A2. The only maybe so it's clear like everything about this definition is fairly normal. It's saying that it's a complete basis. If I give you any unitary on K qubits, in particular could be on less than K qubits also, right? Because it could just be identity on the mean. If I give you any such qubit, you will be able to find some finite and a delta, which is my approximation parameter. You will be able to get delta close to that. The only thing is about what is this Z doing, and that is just for our convenience. The point is that a unitary and multiplying by a phase are the same thing. Phase doesn't matter for us. So therefore, it's not. We don't want to necessarily approximate the unitary we are given. We are happy if we approximate any multiple of it, any unity that is a multiple of it. So for every delta, we might be actually be approximating some different multiple, which is fine for us, because the only things that actually matter for us are the phase doesn't matter. So that's the only thing. Okay. So in a very mathematical terminology, the point is that what you're trying to do is to not approximate it in the unitary group, but the unitary group quotiented with the unit cell. That's roughly what's going on. Okay. So that's what a complete, that's a definition. So it's a definition of a complete basis is that fix a K, it's a complete basis. If every unitary on K, it can approximate to arbitrary accuracy. Fine. That's definition of a complete basis. So the next question is, does a complete basis exist? Right? So it would not be useful if it did not exist. So yeah. So I think Kitai was the first to show that this thing. Yeah. So Kitai in 97. Showed, I think he showed it earlier. This paper is from 97. Showed that the following. So I have to just give the list, right? So the list is, it has Hadamard.
Did you put that here about one C naught and
No, I did not.
where do you put that?
I was not trying to do it in this class. The proof is, it's not something I can do over top screen, but it's not that complicated. This one, it's like this thing of like you keep rotating out things that you try to create diagonals, like you try to sort of basically, it sort of looks like doing Gaussian elimination.
That should appear.
Yeah, these ones are deeper. The next two. They're more sort of, they require the structure of this group. They use more power. So there's one more I will write down after this, which is, and then there is what is called the phase gate. Phase gate. This is I, and therefore also its inverse. Which will be 1, 0, 0 minus I. This is Hadamard. Then control not. This we have already seen. So it has to contain all of this. And the only one gate that we have not seen so far, which is so-called Toffoli gate. It's like a reversible version of AND. So this basically, so what it does is that on A, B, C, it maps it to A, B, C, XOR A and B. So what will 0, 0, C go to? It just go to 0, 0, C. 0, 1, C will also go to 0, 0, C. So 0, 1, C. 1, 0, C will also go to 1, 0, C. 1, 1, C will go to 1, 1, C XOR 1, which is just the complement of C. So in terms of circuits, this is written like this.
The previous result said you just need 1 2-qubit gate and like the 1 qubit gates.
Yeah.
This is a 3 qubit gate.
Yes. Yeah. So I'll say why. Yeah, if you like, you can also go for a. This is how this thing is usually written. CLS topology. Yeah, so as you pointed out, this is what is, yeah, so this is the complete basis. Hadamard, S bar, control node, and topology. The you can base topology by something called the pi by 8 gate. It's a two processing gate. Okay, in the sense that then yeah, pi by 8. So it's like a yeah. Basically, you can think of the phase gate as being a pi by 4 gate because if you like, so what is it? It's like 1 and e to the power I pi by 2. But if you now like what am I trying to say? Yeah, forget about the tiny thing. Yeah, but there's basically like if you instead of the I, you also put an e to the power I pi by 4 there, then you can get topology also out of it. So but yeah. The reason to keep topology here is for one thing, firstly, it looks simpler, like there's no complex numbers in it. The other thing is that it's also complete. So if you want to do classical computation reversibly, in the sense that you want to compute so it's clear. So basically the typical Boolean function need not be reversible, it need not be invertible. But any such function can be made reversible. So basically what you can do is that instead of writing just so you have a function f, you can now convert it into a function which takes x and y, and then it maps it to x goes to just x, and y goes to y XOR x. Now this is a completely reversible version of the same function. That's all the power goes in the function. And in principle, by putting y equal to 0, you can read off of x. So any classical circuit can also be converted into a reversible circuit. And if you want to do that, all you need is a NOT gate and a topology. So basically NOT and topology is complete for classical reversible computation. So the same tool that gives you AND or NOT will also tell you that NOT and topology is sufficient to do reversible classical. So yeah, so that's it's saying that this is basically like trying to keep the classical complete thing there and whatever else you need. So this is the basis, right? So compute. And here is another just a curiosity about topology. This is the result due to it's called yes, so, some of these results will have funny names in the sense that the result I'm going to talk about is called Gottesman-Nil theorem. It appears in the paper of Gottesman, very grateful. So he calls it Nils. So these kind of things somehow in the early days happened a lot where people prove things that they never wrote down. So the Gottesman-Nil theorem. Gottesman-Nil theorem, which Gottesman calls Nil theorem, is so actually it's a slightly stronger than what I'm going to write down, but so this is also called a standard basis. So this is this often called the standard basis. So any quantum circuit which starts in 0 to the n, like basically the initial state is just tensor product of zeros, applies Poly n length sequence. So I'm writing it really informally of gates from the standard family except the Toffoli gate. So it can apply any other gate. It's not allowed to apply Toffoli gate, and it's a polynomial. And finally, any quantum circuit, so it starts in the zero. This is going to be standard actually. Any quantum algorithm, we will have to sort of start it in the 0 to the n basis, because that's the thing we hope can prepare. Then we apply some sequence of the gates. Then we measure in this. The only restriction that is being put is that you're not allowed to use Toffoli. And their claim is, so what do you think the claim would be? It can actually be simulated. Poly in time. Very classical. In some sense, it has identified the minimal set. You drop one thing from it, so there's at least one thing in it, which if you drop from it, it becomes only as powerful as classical randomness. So there's none of the other things are actually restrictions. In all quantum algorithms that we will do, we will have these restrictions. Because this makes sense, right? You are saying that we are only able to prepare initially in the 0 to the n basis. There's no cheating. You cannot just prepare some arbitrary state. Then you are allowed to do some computation on it. And finally, again, you are allowed to measure only in the computation of this. I mean, there's one thing that you are sometimes allowed to do, which is to just take measurements in between and use their results to apply to certain gates. But this can also be some sort of move to the end. That's not a problem. So, and this theorem holds even that. So you can strengthen the theorem so that like you can even do measurements in the middle and based on the results of those measurements, decide which gates to apply. That is also allowed. Still this theorem. So yeah, so basically without this, this standard base is sort of in some sense quite parsimonious. Like you drop one of the gates from it, which is the Toffoli gate, it becomes only as powerful as something. Okay. So this is one thing. Okay, so far what have we done? So we have seen that there is some that there is a complete basis, and complete basis means that any other gate can be approximated using this U. But the complete basis definition, remember, did not put any quantitative bound at all. Right? It just said there's some number and then you do a. It did not say that this delta U is of a certain length, polylog and this and that, right? Right? There's no quantitative claim in the complete basis definition. That is clear, right? Yeah. So here is the other sort of maybe deep result, which is some analog of. I am solving. And again, it's again this thing where Soloway had proved it but never wrote it down with a person solved. So it does something quite interesting, isn't it? Because the notion of completeness has not, I think, quantitative in it. It says that there is so fix. Uh, so this is actually something people work on. If you can improve this three, see why, and any complete basis. Yes, uh, and arbitrary finite f of quantum cubes. Okay. So then, so this depth and size are here in the quantum that are positive. Again, the depth will be just how many, like, if you go from the left to the right in the circuit thing, how many gates do you cross? The maximum number of gates that you cross line, and the size will just be again like the number of wire segments. In this case, you can also think of it as number of gates because they are within constant factors of each other. If the gates are all small, like all of constant sets. So, but yeah, the right correct thing is to count the number of segments, like wire segments. That's the sense. Then any circuit C of depth D and size L using the size is number of wire segments. Using Gates can be simulated up to C delta by a circuit C prime of okay. So it's a sense here is again the same thing, right? So I mean both of these are unitary. Which uses at most order of L times log of L by delta to the power u. So it means Gates Gates all from and yeah. Then call course depends depending upon which on input C produces in time. Like by produces C prime, it produces a description of C prime, like where, like drawing of C prime in time, some K prime. K prime is prime. But its constants depend only upon the point is the constant depend only on S, F, and U, not on anything else. Yeah, so the nice thing about the theorem is that it also gets you a quantitative form. Well, of course, they're constant, but other than that, gives you now reasonably efficient kind of simulation. So it says that any complete family actually simulates quite well, like any other complete family.
Can you show the whole theorem on screen?
Yeah. Okay. So new think of X as just some number bigger than 3, fix 3.1. Okay. Any complete basis S. So it says that you take any complete basis S and an arbitrary finite set. Yeah, for quantum gates. So write your circuit C in this finite set, and you have some depth T and size S. Then someone else can come and produce a circuit of depth and size not much long. I mean, so now notice that there it was a size, which is the number of segments. Now it's about gates, but that's fine because the complete base rate is a finite set. So these things are within a constant factor, which are in size.
Is mu number of qubits?
Which one? Where is
What
mu?
is mu?
Where is mu?
Uh,
No, mu is just a parameter. It's just think of it as 3.1. Any number bigger than 3 works. So that is like a yeah. Ideally, we would like to make mu as small as possible, right? But the Kita group gives you any number bigger than 3 will get you out.
And the theorem statements makes no mention of number of qubits.
No. All of that is implicit in the size and the
Okay.
size and the depth. So it takes a circuit, so certain size, certain depth. It produces a circuit of comparable size, comparable depth. The loss is log L by delta to the power mu. Mu is about 3. There is work, I think, ongoing work on trying to improve the 3. I don't know what the current state of the art is. So this is saying that all you have to do is show completeness. Completeness had nothing about quantitative, just that it was basically a density statement. It was saying that I can go arbitrarily close to any point you want. That's all I wanted. But now it's like, okay, if you can do that, we'll actually also do it efficiently. So that's where like the properties of the group come into picture. So anything that is producing a dense set by multiplication should actually be doing it quite quickly. That is. Okay, so for us the point of this thing is that okay, so we can just stick with any finite number of gates, and if we get polynomial size, polynomial depth, then it's fine in the sense that in the complete basis, some arbitrary complete basis that anyone else had, the depth and the size will not increase by 2. And you by polynomial factor.
By any complete basis.
So because the point is that maybe for your so like already we saw 2 examples. I mean, I wrote down only one, but for example, you can replace Toffoli by this 5 by 8, and which complete basis you choose might depend upon your implementation details, right? So in some particular implementation, a certain complete basis might be easier to. So whereas for your algorithm design, something else might be easier to look at. So it is saying that at least from the complexity point of view, it is all fine. You just choose some fine stock gates, write an algorithm in terms of that, and then this theorem will guarantee you that if someone, at least in the practical sense, these log things can still be pretty bad, but at least at the complexity theoretic level, it is saying that it doesn't matter. You choose your favorite finite family of gates, write your algorithm in terms of that, and think you only change that small. So this is it's changed by a polylogarithmic factor. So this is in some sense the analog of number 3. Okay. So at least from the complexity theory, these from the complexity theoretic. In arbitrary fixed set of f of gates. So this fixed set is important, right? So this setter should not change with the instance size or the input or anything. It should be fixed in advance. That is important in theorem. Terms of circuit size and depth can only change by polylogarithmic factors, right? Because whatever L or D I had, I will only change it by polylog of the size. Okay. The original gates that you choose, of course, need not be complete or anything, right? I mean, you could choose some smaller set also possible. But you write it, and then someone else will have a complete list because they have system. And, so this is some analog of. Okay, so we'll not look at this in detail, but it's good to set it up because so this is a sort of a foundation. Like that's why you can look at arbitrary finite gates and distill to quantum complexity theory, and there still be like at least in terms of at the level of checking whether something is polynomial depth, polynomial size or not. This is all fine. So from now on, the upshot, so we'll not look at the the theorems are actually, yeah, especially the Kitaev-Soloviev theorem is quite, yeah, these are all non-trivial theorems. And but for us, the only effort will be that we want to, that as long as they're working with a finite fixed set of gates, compressibility we fine. Any estimates we get on the size and depth will sort of change only slightly in going to other. So when we are doing, for example, factoring, we will work with some fixed family of gates and we will do the thing, and it will be polynomial in the representation of another, and it will remain polynomial if someone goes to some other case because okay, so this is saying that it's quantum complexity in some sense does not depend upon which standard basis you start with, which complete basis you start with. So this foundational thing is. Okay, so any questions about this? Yeah, this went fast, but this is more like I think, journalistic thing where I just wanted to say what the results are. The exact parameters are not important. For us, the only thing that is important is the loss is only polylogarithmic. Thanks. So any questions so far? If not, then let us change gears and start doing something else. Maybe something more hands-on. So maybe this will not be this will not immediately appear relevant. But here is maybe a question. Question. So let us consider. Okay, maybe before the question. So there's another thing that is sometimes useful while doing things, which is to use this so-called ancilla qubits. So let me just do that also. So sometimes what you might want to do is that you want to do some computation in the standard basis, whatever. But it's sort of not possible. So like so far what I've been doing is we have n bits of input and we produce n bits of output. Now this is almost saying that whatever the amount of input space you get, you're only allowed to operate within that and then produce an output. This is not how classical computing works. There you're allowed to take extra space, do some calculations there, and then finally produce the output. So the analog of this should also be here, because it's clear that there are certain things even classically that you cannot just do in the same amount of space as well. Right? So the analog is this ancilla qubit. So what are ancilla qubits? So this means that what you are allowed to do is you can have the input qubits, and then what you're allowed to do is you can take some extra qubits which are not entangled with the original qubits in the zero state. Then you can do some operation on this big system, but finally you're supposed to output like the original qubits. You're supposed to return them in the same way they were. So you say that like so you say that unitary U implements so a unitary U, which is, let's say, HA tensor HB to HA tensor HB implements a unitary V from HA to HA with ancilla if for every phi you apply to phi tensor 0, phi is in A, 0 is in B, is actually equal to V psi A tensor 0. So nothing is being claimed about what happens if this thing is not 0. It's just that if I start so if my original memory is garbage, I don't know what's the original memory is clean. Then if I do the calculation, then I will leave the original memory in the state it was in, and I will have computed. So this is just sometimes it's useful to just get smaller circuits. And you can also have a version of this with error, right? But let's for now just have this. So you can also have a version of this with error. Please there it is with error delta if okay, so the natural thing for every, this is for every side. Okay. So this is something to keep in mind that you are allowed to do this. You're allowed to take some extra qubits as long as you return them back to the original thing. This is also useful, of course, in the classical world also, right? I mean, like you're allowed to take extra. So even in the circuit model, you're allowed to take extra wires and you can do arbitrary things on them. In the classical case, it's not so important that you return them back. And this is basically because in the classical case, the returning to zero part is trivial, right? You can just set it to zero. This is not possible in the quantum world. Right? Because everything is reversible. No such thing as setting to zero. You cannot forget it. So in the classical world, the analogous thing would be the reversible system. There also you cannot just set to zero. If you set to zero, somewhere else you have to. But there again you can use similar things. So yeah, so to get some familiarity with this, let's try to solve one problem which will be useful. And it's a primitive in something else we'll look at. But here is the thing. So what I want to do is the following. So I want to look at the following initially. Consider, now is the question. Consider the unitary. Q, which is I minus 2 times 0, 0. Right, on C to the D. So this is clear, right? So it is so 0. So by 0 to the n, I mean 0 n times. Is this a unitary? It's claimed it's a unitary, so that's proved by whatever aversion or intimidation or whatever. But is it a unitary? Yeah, you can even just calculate u dagger is just u. That is easy to see. If you multiply it out, but there's an easier way to see that it's a unitary. It's actually just a reflection, right? Basically, what does it do to any vector? It takes its component in the zero direction and changes the sign of that. Take any vector, there's some component in the zero direction, which could be zero also, that's fine. But whatever the component is, this unitary all it is doing is just changing the sign of the component. So it's really just reflection in a mirror. And which mirror is that? Yeah, what?
That.
That it's the mirror orthogonal to the zero. So any mirror is a hyperplane, and this is in high dimension also. So it's described by its normal vector, and the normal vector of that mirror is this vector 0, right? The ket 0 to the n. Right? So this is actually reflection in a mirror. Orthogonal to. That's what it does. It is clearly unity. It's norms in the first. Okay. Good. So can you implement it using so now your goal is the following. Your goal is that you choose some finite set of gates. So finite, of course, means that it should be independent of n, right? And implement this. So let's say you're allowed to use ancillas and such things. Ancilla is allowed. So let's take the yeah. So goal, choose finite set, yeah, independent of n. Of quantum gates. and implement this. Implement U. Using. Wait, everyone knows the O notation, right? O of n means that. What does it mean?
N operations.
Not n operations. It means that it can be brought about by there's some constant c set for large enough n, it is at most cn. Yeah. Order n. Okay. You can use answers. Okay. So it's the simplest thing to do is to just start small, right? So let's try to also construct a set of gates in a flight. So what about n? Like if n is equal to 1, what is this gate? If n is equal to 1, what is this gate? This should be easy, really easy. What is this matrix of this gate? N is equal to, huh?
Minus Z.
Is it minus? Yeah, it's minus Z, not Z. Yeah, it's minus Z. So, but for us, phase doesn't matter, right? So it is, you can as well think of it as Z. Right? So, yeah, so it is essentially this is the same gate as Z if n is equal to 1. So, at least let's keep Z in our thing. So, at least the n equal to 1 case is solved. How about the case 2? N equal to 2. Actually, maybe just to make things slightly easier, or yeah, it doesn't change anything. It's like, let me put it like this. Let me put it like, so it's actually now a reflection in the perpendicular thing. It's like a, so then this is Z. Okay. So now how about case n equal to 2?
Z and Z minus.
Actually, I'm confused which one was easier. Maybe the other one is easier. So let's see. Yeah, I think the other one is easier. So forget about that. Yeah. Yeah, sorry about this. Yeah, that is.
The easier one is I minus 1 to the n 1 to the n. That's how we work.
No, that also I don't want actually. Yeah, maybe that is easier, but let's just continue with this for now. Yeah, it should be fine. Yeah. So because there is none of them are really even more difficult than the other. This also is because
Minus the,
hmm?
minus the.
Yeah. So so let's try to just write on the matrix, right? So the matrix looks like this. It looks like minus one. Yeah, I think maybe that is just take that once. Yeah. Yeah. Now does this look like something? So the empty things are of course zero. What is it? Have you seen this before? It is. I mean, we have not seen this precise one before, but it is should remind us of something. Control Z. It is exactly Control Z. Is that clear? Why? So let us see. So it's actually Control Z. And so what does Control Z do? So let's look at the operation of this. So let us call this circuit A for now. Then A 0 sorry A B is just A P and it is actually just minus 1 A. A and here goes 1. Put some minus. That you can just check. And the other reason why it's Control Z is you know it's like so when it's like so this part, the top part corresponds to the control qubit being 0. This part corresponds to it being 1. And so when it is 0, it's acting with like identity. When it is 1, it's acting like Z. That's exactly what a control. So yeah. So basically, yeah, another way of thinking about this is that this is that's what it's controls. Okay, so Control Z. Now it seems like we have to put Control Z. We don't want to use Control Z, right? We want to probably put Control X in it. So one question is, so here's an exercise. Maybe this is where I'll stop. Show that control that. So this is actually let me not call it A. Let me just use the notation we have been using for control gate, right? This is called lambda. Lambda, right? Lambda is the control. Okay. So that this lambda Z can be implemented using control X, this C naught, and 2 around. This should be easy because we have already done this actually in some. I mean, like you've done it for the X and Z thing, so it should be very easy what to do. In fact, in the circuit model, it should be immediately clear what to do in the circuit diagram. Yeah, but maybe we'll do the next class. So that's it. And once you have this, then maybe you will get the hang of this. You have to use the poly. But yeah, it's just. Yeah, and then once you're done with this one, try to implement the original one, which is I minus 2, 0, 0.
Do you need to follow for this?
For which one?
For this one?
For this one?
Yeah,
No, this is just two elements and central X.
no, for N, right?
Yeah, and I think you do. Or at least I don't see how to do it without topology. Like even just the classical case, right? I think someone may need the control and maybe some no and. So I just want to do the classical version of this. So this also can be seen as a, so I mean, these are a very nice kind of operation, right? It converts it's the permutation of the, this is almost like a classical operation because it takes all the I mean it's not quite because of the sign, but it's sort of like basically it is applying a function, right? You can think of it as like for every so what it is doing is a complete diagonal operator. So on every diagonal, it's applying a plus or minus depending upon its value. So it's sort of like exactly like a classical operation. So it should be analogous to trying to compute the classical function, like the full AND basically. And that I think you need at least 2 qubit AND. You cannot just do with it. So that's. So is that, yeah, so the thing I was saying is that if you look at the matrix for you, in the general case, it's a diagonal matrix. It has -1s in some places and 1 at some places. So we just think of it as a -1 to the power some Boolean value. You're basically computing just a classical value and then putting a -1 there, wherever, like -1 to the power of classical function. What is the classical function? It is exactly the AND, like the AND of everything. And in the classical case, you can show that with just XOR, you cannot do AND. So you need the AND, you need 2 bit AND or and so that. Okay, we'll stop here.